Hi, it's Daniel Brown, and in this video we're going to talk about the Black-Scholes-Merton model. So our goals are to talk about the assumptions behind the model, the intuition underlying the model, and the actual formula. So first, the assumptions. Now this first set of assumptions are strict. So these need to be true for the Black-Scholes-Merton framework to be true. These are standard assumptions we make when we're thinking about derivatives. So first, there are no arbitrage opportunities. One can borrow and lend at the risk-free rate. One can buy and sell the underlying asset in any quantity, including fractions. One can buy and sell the underlying continuously. And finally, there are no transaction costs. Now, clearly, none of these are strictly true. So of course that means the Black-Scholes-Merton framework is not strictly true either, but we live with the imperfections in the model and the imperfections in the market. So the Black-Scholes-Merton framework is a reasonable framework, but we've got to know that we're making these assumptions when we price our option, and if these assumptions aren't true, then our option price is not going to be strictly accurate. Okay, second, we've got some assumptions which are a little bit less strict. So constant interest rates, constant volatility, and no dividends. So all of these can be relaxed when we're trying to price European options, and the framework still works. So when the framework was originally set up, one made these assumptions. Now these assumptions have been relaxed and we can still work within the framework. We have to make slight modifications, but things still work. Okay, the last one is the stock price. So let's take a stock whose price is S, and we're going to assume that in a short period of time, of length delta t, the log return on the stock is normally distributed. So the natural log of S sub delta t, the stock price at time t, we of course, or time delta t, we of course don't know that, divided by S is normally distributed with mean mu delta t and variance sigma squared delta t. Okay, so mu is what's called our expected drift, and sigma is the volatility. Now what this implies is that over a longer period of time, so lots of little steps, the natural log of the stock price at time t divided by S is normally distributed. Now there's this adjustment to the mean. So the mean is mu minus sigma squared over 2 times t, and the variance is sigma squared t. So what you see in this is that the drift assumption gives you a slightly different mean return because of the volatility. Now, the logarithm of st is normal. That means that st, the logarithm of st, or the returns are normal. That means st itself is log normally distributed. And a log normal distribution looks kind of like this. And we often don't draw this, but if you step back and thought about your standard finance class, you'd be in the same sort of place. Okay, so let's just take a step back though and actually think about those standard finance assumptions, because these are a little bit different. We have this drift term rather than an expected return. So assume we have a stock, and we assume that at some time t, we model the log returns of the stock as normally distributed with an expected return and a standard deviation of this return. So this is what we normally assume about our stock. So that could be 6 months from now, we expect to make 12% on the stock, and the standard deviation of that 12% is 20%. So this is the same as assuming the stock is log normally distributed, where natural log of st over s is normally distributed with mean, expected return, and variance standard deviation squared. So to convert, we simply set expected return equals mu minus sigma squared over 2t, and standard deviation equals volatility sigma times square root of t. So in order to do this, we find the volatility first by taking our standard deviation and dividing by square root of t, and then we can use that to find our drift, expected drift. So you've modeled the log returns of a stock in 3 months as normally distributed with an expected return of 12% and standard deviation of expected return as 20%. We want to find the equivalent expected drift and volatility. So first we find the volatility. Volatility is standard deviation divided by square root of t, which is 40%. The expected drift then is given by expected return equals mu minus sigma squared over 2t, or mu equals expected return over t plus sigma squared over 2, or 56%. And again, it's a big drift because we have assumed that in 3 months we're expecting to make 12%, so you need a pretty significant drift in order to get that. Okay. In the derivatives kind of assumption, where we're assuming expected drift and volatility, we're modeling our stock. This thing is called a Brownian motion. So we model our stock with an expected drift of 10%, volatility of 25%. Current stock price is 75. We want to know what the 95% confidence interval for the stock price in 3 months. So the expected stock returns are normally distributed with mean 1.7188 and standard deviation sigma squared of t, which is 12.5. And we want to find the 95th percentile, 95th percent confidence interval. So we compute the 2.5% return using norm.inv of 2.5%, comma the mean, comma the standard deviation, negative 22.7807. And the 97.5% return, doing the same thing, norm.inv of 97.5, mean standard deviation, 26.1283. We can compute the stock prices using S, E to the return, and the 95% confidence interval is 59.72, 97.48. So again, we can use a bit of Excel, cumulative normal functions, inverse cumulative normal functions to think about the distribution, and we can work back and forth between the standard finance kind of assumptions, expected return, standard deviation return, and the standard derivatives assumptions, which is expected drift and volatility. So it doesn't really matter which one we work in, we just have to be comfortable getting back and forth between the two. All right, the intuition behind the Black-Scholes-Merton framework. The intuition is once we've made all of those assumptions, the only risk that an option has is the asset. If we go back to the binomial tree, remember with the binomial tree, that's essentially what we were making. We're saying the stock could go up or the stock could go down. In the future, we knew the value of the derivative, d sub u and d sub d. We have these risk neutral probabilities to find the price of the option today. But the real key in the binomial tree pricing is this delta. And when we created a portfolio which was long the option, short delta shares, what we found was that there was no risk. We didn't care whether the stock went up or down. Now, the way the Black-Scholes-Merton framework works is it makes this time step, the delta t, infinitesimally small. Each instant of time, we create a portfolio that has no risk. If it has no risk, we earn the risk-free rate. Every instant that goes by, we rebalance our hedge when the market moves, right? The stock goes up or the stock goes down. Now, of course, we're working in a world where the stock can go anywhere. The return's normally distributed, but still over that very, very small piece of time, we earn the risk-free rate because instantaneously we have no risk. Okay, last but not least, here are the formulas. So this was first published in 1973 in a paper by Black and Scholes, The Pricing of Options and Corporate Liabilities. Robert Merton called this the Black-Scholes option pricing model, and the model gives a formula for European option prices. Now, Merton, MIT, and Scholes from Stanford received the 1997 Nobel Prize in Economics. Black did not because he died before 1997, and you can't receive a Nobel Prize if you're not alive. Okay, so I probably have these formulas memorized or nearly memorized. I'm pretty good at them, although I don't use them that often directly. I do not expect anyone to memorize these formulas. There's no value in memorizing these formulas. The goal is to understand the formulas, understand what they're telling us. But you should see them at least once. So this is a European call price. This is a European put price. So the European call price is the stock price, S, times N of D1, so N is the cumulative normal function, minus K, e to the minus RT, so that's the strike discounted to today, N of D2. Put is K, e to the minus RT, N of negative D2, minus S, N of negative D1, where, here we go, D1 is the natural log of S over K plus R plus 1/2 sigma squared T divided by sigma square root of T. And D2 is D1 minus sigma root T, this mess. Okay, these are messy formulas. Inside these formulas is the cumulative normal function. So this is the standard normal cumulative density function. It's the probability that a normally distributed variable with mean 0 and standard deviation of 1 is less than x. We can do this with one of two Excel functions, norm.dist of x, 0, 1, true, or norm.s.dist of x, true. Now, we'll go back to our formula in a minute, but again, pictorially, we've got a probability density function, the red line. We've got the cumulative density function, the blue line, and for the people who have some calculus, the blue line is the integral of the red line. All right, let's go back to the formula for a second, just to take a quick look. D1 and D2 are a little bit strange. We will investigate them a little bit more. But if you stare a little bit, first off, the variance of our return distribution was sigma square root of T. Sorry, sigma squared T, standard deviation, sigma squared of T. So D1 and D2 look a little bit like z-scores. They're not quite right, but they look a little bit like z-scores. We could rearrange them a little bit so they were z-scores. So we'll come back to that in a little bit. Okay. Now, the key thing to note about the Black-Scholes-Merton formulas. The variable mu, that was our expected drift. The expected drift does not appear in the differential equations, which give us these formulas, nor does it appear in the formulas. The equation, the formulas, is independent of variables affected by risk preference. So it doesn't matter what we think the stock is going to do, is the key here. In fact, we could get to assume, or one way of looking at this is we get to assume that the stock returns are the same in the risk-free world, so there's no risk, as they are in the real world. So this is called risk-neutral valuation. Now just to finish up, and again, it's worth being able to do this. Generally, I would build this formula into Excel as opposed to doing it on the fly, but we want to find the value of a call option with strike 25 and maturity 1 year. Market date of spot of 24, risk-free rates of 4%, volatility of 25%. So I'm going to cheat a little bit, have my formulas in front of me. Let's bring up Excel. Okay, we've got our Excel spreadsheet. Let me put my information into the spreadsheet first. So we've got our option data, which is going to be our strike and maturity. If you know me, I care about formatting. So the strike was 24, the maturity was 1. And then we've got our market data. Let's set this up. And we've got spot, risk-free rate, volatility, there we go. So let's set this up. So spot, well, the strike was 25, spot was 24, risk-free rate was 4%, the volatility was 25%. Okay, so to price, why don't we do over here? We need D1 and D2. So let's see here. So D1 is natural log of spot divided by strike plus the risk-free rate plus the volatility squared divided by 2 times the maturity divided by the volatility times the maturity. So that's D1. And D2 is D1 minus the volatility times square root of maturity. So we want the cumulative normal function. Let's format these nicely. Heading 2, these are calculations because we don't care what they are other than they're right. So n of D2 is norm.s.dist. Sorry, n of D1 is norm.s.dist of D1, comma true. And n of D2 is norm.s.dist of D2. And the call price is, let's make this an output, S times n of D1 minus K times e to the minus R T, that's the discounted strike, times n of D2, 2.379. So that's our call price. So again, I very rarely do this by hand. Most of the time I've got a calculator which takes the information on the left and calculates this number, 2.379. One thing to note about the pricing here. In fact, let's just do this. Let's make this calculations. Just make our spreadsheet look a little nicer. There we go. Okay, so one thing to note. When we trade an option, the strike is fixed, obviously. The maturity is fixed, but the maturity is not really written in years. So the maturity is fixed, but if we think about it, the maturity is a particular date. So as time passes, the maturity on any option is going to get shorter, right? So it starts at 365 days, then it's 364, then it's 363, and so on. So maturity changes if we look at it in terms of years. The right way to think of it is an option matures, a European option matures on a particular date. Second, market data. These numbers, again, the Black-Scholes-Merton Framework assumes that the risk-free rate and volatility are constant, and the only thing that can change is spot. If the other numbers can change, then our model's not correct.